Hi everyone, how are things? Welcome to the ultimate RAG tutorial. This is the most extensive detail and hands-on tutorial that you will probably find anywhere on internet, which tries to explain retrieval augmented generation, aka RAG. This tutorial aims to make you experts at building solutions and applications which leverage the generation capabilities of modern large language models. So, let's go. So let's start with ground zero, or so should I say, where RAG system became as popular as it is today. So retrieval systems are an age-old concept anywhere in your daily life where you might work with a sophisticated system and interact with it in natural language or pseudo-natural language to access useful information is a retrieval system. Some examples are search, it's a retrieval problem. Accessing a database using SQL is also a retrieval problem. So yeah, though retrieval as a discipline of science and tech has been under study and application for ages, but what made it so popular in last 1 to 2 years is the advent of age of large language models. So large language models, or GPT-4, took the whole world by storm in 2021. What actually amazed everyone was we now had a system which we could interact with in natural language and could get a human-like response. Moreover, these language models were excellent in terms of information tasks like text summarization, code generation, cross domain knowledge transfer, understanding multimodal responses, and so on. Though the initial experience was outstanding, when teams planned to deploy this into enterprise or production applications, they learned a big flaw about them. The problem with LLMs is that they have been trained on openly available data like internet blogs, Reddit forums, Wikipedia, open research papers, open domain books, etc. That means they do have a good understanding of how the world works or about general knowledge like which country is Paris in, so they make an excellent general knowledge retrieval systems. But when it comes to domain specific or deep knowledge like healthcare, insurance, banking, or organization specific knowledge, they don't have much of a knowledge base to rely upon. The problem is particularly grave when someone is trying to deploy an LLM for a knowledge retrieval task, which is for an institution or domain which has its own proprietary knowledge base for organizational function. Let's take an example to understand it better. If you ask ChatGPT, what is the capital of France? It answers it with ease. But if I ask it, who is responsible for approving home loans at XYZ bank, it might not answer it, or it might what we call hallucinate. It might give an answer which is totally random. Now, why is that? It's because the answer of the question that who is responsible for approving home loans at XYZ bank is probably in one of the documents deep within the knowledge base of XYZ bank. So this failure of LLMs raises a deep concern around how to deploy LLMs for domain or organizational use cases. The answer is Retrieval-Augmented Generation. RAG, or Retrieval-Augmented Generation, is the process or protocol through which we enhance the knowledge or context of an LLM, based on which we can help an LLM answer questions which are either not in its knowledge base, or LLMs find it hard to access that knowledge base. The intuition that you might want to build to understand a RAG-powered LLM is that a generalized knowledge base of an LLM is like its long-term storage. It stores world knowledge which it has been trained on. Now, when we expect an LLM to solve a problem, or when you ask a question from an LLM, the LLM tries to access this knowledge base of this long-term memory, but that knowledge either might not exist in the long-term memory, or the LLM might find it really hard to access that knowledge snippet, due to which it might either not answer the question or hallucinate and give a wrong answer. Now, RAG adds a short-term memory or RAM to a LLM. Based on what question is asked, the retrieval system adds knowledge which is tailored for the existing question to LLM's current context. It makes it much more likely we will have an accurate and productive interaction with an LLM. Let's understand this much better by building a basic RAG pipeline. Alrighty, so let's get started with this short implementation of a basic RAG system. The idea of this small tutorial is what more points were discussed before in this video. We'll try to see that in action and see a simple retrieval augmented generation in action. So proceed with the code and implementation and everything else. Let me move this here. Now, this is a simplistic architecture of a RAG system, okay, which works with large language model as a generator, and the large language model is supported by a retriever and helping it enhance its current knowledge base. Okay, so if you see the way it might happen is we'll take an example of some of the things that we discussed before in the video. Is suppose the user asks a question about the who currently manages the lending in XYZ bank. So this question goes to the retriever. Retriever takes that question, goes to the current knowledge base of the XYZ bank. The assumption is this retriever and this complete application is for an XYZ bank. It fetches the corresponding document that might be needed to answer that query, take the document and adds the retrieved context to the context of large language model, and then the large language model takes that context that has been added to its overall uh, next token response context numbers and helps us generate a response. Okay, so this is in if you try to understand it, this is how the complete retrieval augmented generation mainly operates. Okay, and then everything right from a basic RAG application to advanced RAG application is in essence this. Okay, then there are nuances, and as we have discussed before, and as everyone knows, nuances are what differentiates between a great implementation to an implementation that works very well on a notebook or a computer, but doesn't well that well on a production. Alrighty, let's proceed. Now, the first is let's probably pick a use case. The use case that I picked here is we will build something that is called as archive bot essentially. So online, we do have archive.org where there are like lots of free peer review and sometimes peer review research papers are uploaded. And we do have a data set essentially, which is called, let's have a look at it. Okay, it's called the archive metadata, OAS snapshot. We can even try and have a look at it. Archive data set. Okay, so this is data set that I spoke about. It's on Kaggle. Everyone can go and download it. I will mention this link down below in the description. Feel free to check this out. So yeah, what I've done is I've downloaded it. I've unzipped it, so it gave me a JSON which was around 4 GB in length. And just to check what actually exists in there, this is a function that we have written which helps us see multiple records within the archive file. Let's have a look at it. So yeah, we're looking at three. This is the complete structure of the JSON document. It has an ID, it has a submitter who actually uploaded that particular research paper. Then we have a title of the research. And post that, we also have the abstract of the research paper. Alrighty, so this is what we have for n number of research papers in there. And this is going to be our knowledge base based on which we will have developed a retriever, which will be leveraged to add context to the large language model. Alrighty, so and that what I'm calling it is an archive bot, which could be probably leveraged by anyone trying to understand more about research paper or ask questions about research papers and so on and so forth. So very simple case for us to just to understand how retrieval augmented generation essentially works. Now let's move ahead. Okay, the first one will is try and understand basic retrieval without LLMs. Right, as I mentioned before, retrieval is a very old, very age-old, tried and tested engineering and science skill. So we'll first of all try and develop a basic retrieval based on this data set that we saw. Step one, we create an index and get term frequency, inverse document frequency for each article or abstract. Okay. Now, what is a TF-IDF or term frequency inverse document frequency? Let's check that. So this is a link that I have shared. Please feel free to check it out. But in essence, a TF-IDF is a way of identifying that out of a text corpus, if we have different words, after removing the stop word like is, are, the, how many words exist in that word, in that statement, which are very unique to that statement, but not uh, are not present that much in the rest of the corpus. Okay, so this is called a term frequency, inverse document frequency. So I would mention here, term frequency, where we're looking at the frequency of particular term, you're concerned with related document. There are multiple measures. Okay, and inverse document frequency looks at how common a word is amongst the corpus. Okay, so so we see if to term frequency, we see if there is a word which is mentioned multiple times in a particular, let's say, statement, but it's not mentioned that much overall in the corpus. It's become a very important part of that statement. So to calculate TF-IDF, we basically multiply both of them and kind of get something called as a TF-IDF score. So in a sense, I won't talk more about it because it's a very simple concept. Please feel free to read through it. But that's what we are going to do. That's what we are going to use to create an index. And we'll create an index and then we'll get a TF-IDF for each article or abstract. This is the code that we will use. What this code essentially does is it takes the document, it for each line essentially in that document, or for each pooper in that document, it loads it using JSON load. It kind of creates a particular text field by appending the article and the abstract together. So this is what we will use to for each paper. We will have the article and abstract and title appended together. But that is what's going to be used to calculate TF-IDF. Suppose that we will also have something called as metadata, in which you will add the title and abstract. And finally, we will use something TF-IDF vectorizer. Again, scikit-learn, a great library. Lots of people who are probably from the data science world will know about it. Is used to vectorize all of these documents. Okay. Now, which we save it as a pickle file. So that's as simple as it is. Essentially, like each paper is taken and its title and summary is appended together relative to the all of the everything in the in that JSON file. We calculate its TF-IDF score and we store all of that. Okay. Now, final thing that we have, as I mentioned here is a pickle dump. In that pickle dump, what we have is for each paper, we have the vectorizer, we have the 2F-IDF matrix, and we have the metadata. That is what we have stored, but we are mainly concerned with the vectorizer and the metadata. So in here, basically, when we run it, I already run it before. It takes a bit of time. It's reading the documents in here. It's probably a few more seconds. Suppose that once this gets done and we have the vectorizer for each of the papers, we'll create a simple user experience, user interface using Gradio, a really popular interface creation tool for people who don't want to develop a full-blown user interface using JavaScript and React. Alrighty, so it's done. We have the index created and saved. So our very important part is done. Now let's basically run this, create the interface. All right, it's loading the index and hopefully creating an index for us. Alrighty. Archive paper search using TF-IDF. So as I mentioned here, let's search for something. Let's search for probably, I've been reading a lot about dark matter. Let's search dark matter in planets. Okay. Remember, right now it's just doing a text search. Okay. Text search in a different way, but in essence, it's a text search. It takes the words and what you are asking for, and all of the corpus that it has, it goes and tries and find those words, and it has a way of basically wherever it finds those words which exist, is basically will rank them in a particular way that we mentioned, cosine similarity, and present to us. So I mentioned dark matter in planets, and I've clicked on submit, and here it's processing it. Let's see the results that come out. Okay, we got some results. Alrighty, so let's go right to the top. Okay, result one is dark matter and the habitability of planets, and gives an abstract. Okay, not bad, right? I searched for dark matter in planets, gave me the first one was that. Result two, light dark matter accumulating in planets. Not bad. Result 3, unified distribution of dark energy and dark matter. This doesn't have planet, so therefore it got a lower score already. So you got in essence how a basic retriever or text-based retriever might actually work. Again, right now it's just a retriever, right? So one thing to understand it still doesn't have a conversational quality. Why are large language models so popular? Is because you can have a conversation like a human to it, and you don't need to have a binary coded answers to it where every time it will respond in a particular way. It's literally has a bit of dynamic way of answering questions, but also you can add a retrieval to it. Like giving an example, if in here I ask a question, can you recommend some papers on dark matter? Alrighty. So if I ask this question to a few of my friends who are physicists, they will probably say, "Oh, yeah, definitely. These are the 3 papers, right?" Or, "Oh, yeah, sure." Something like that, right? But when this is something just which is a retrieval system, so it highly won't. So I will click on submit. Okay. Shut up and let me think, or why you should work on the foundation quantum mechanics as much as you please. Just looking like it's very likely, okay, whatever, and so on and so forth. We don't have anything here. Introduce and work on dark matter. Okay, we found something on dark matter. Solar system. As you see, what we just got as results. We didn't get a conversation. We didn't get a further details around it, and that is why we basically introduced large language models into our workflow. All right. Now, next move forward, and let's try and build a large language model powered chatbot on the same corpus that we basically saw before. Okay. So again, the whole code is in here. I have written this code to run on Azure OpenAI, but the same code can be leveraged if you are using it for OpenAI or you are using even it for Anthropic. The models underneath don't matter that much. The prompting and the corpus actually matters at this simple scale, at least. So simple code. Again, as I mentioned, I'll just quickly run through the code. It takes the pickle file, takes the vectorizer, takes the TF-IDF of the matrix, searches through the whole of the corpus, and gets the corresponding result, takes the top result, top paper that it could find, and adds its title, abstract, and the corresponding cosine similarity score to the context of the large language model, right? So here is a retrieve model, so basically joined in here. And then you have something that is called as a system message. A system message essentially is where you tell a large language model how it should basically respond. So it's a simple message. It's basically you're an archive bot and you do some stuff, but your goal is use the information from the papers. Only mention limitization if the paper totally contain no relevant information. If paper partially addresses the question. So ideally, one thing that you have to understand is now you have to play with multiple stuff, because the large language model, in essence, it also has its own information. So you have to explicitly mention that it should use the context or the information that you are adding from the retriever system. So there's important pointers around it essentially, which I've kind of mentioned here. Feel free to use it. Feel free to further enhance it. Again, working with the prompts in a very good way is another huge topic. We might have that also a topic of discussion sometimes later in another series of lecture. Another thing that we do is we also add a chat history. So chats keep on happening, and we want to make sure that the large language model has the context of the conversation that we have happened so far. So we keep on adding the chat history to the conversation that we keep on having. So that's about it. I think that's what we are doing. We're just playing with the large language model here, and we kind of launch another Gradio UI. It's loading the index. Hopefully we should have the UI anytime now. The fun part is, and the most interesting part of the whole process that I find is that how much large language models have made us take human-like conversation with a system for granted. Like when I was doing this retrieving thing before, which doesn't have a large language model, I was feeling, oh wow, it's so outdated. But it does the job, right? It does the job, but this human experience, the user experience that you get here, like already. So let's ask it a question, please. Papers on dark matter. Okay, let's see. I'm asked you to please recommend me some papers on dark matter. We have a large language model in the backend. Let's see how it answers that. Okay, here we go. Here are some relevant papers on dark matter that you find interesting. Comments on recent work on dark matter capture in solar system. Unified distribution on this, and you see how it has formatted it for me. It has not just taken a chunk from the dump and put it in here. It has basically formatted it like how a good conversational agent or a good person who's a knowledge expert where it might put it in. And I will Apple full edition. So again, see papers, I can further ask it other insightful question. We ask it which of these papers I should start with. Oh, please mention also mention why. Okay, I got about an answer. Okay, among the papers mentioned, I recommend starting with the unified distribution of dark energy and dark matter. Okay, so before it kind of gave me 3 papers. Okay, and the second question that I asked is which of these papers I should start with, and please justify it. And if it was not a large language model, it would have never been able to justify stuff, because here it's bringing its own internal knowledge with the addition context that I have. And so it's given me, okay, you should probably use unified distribution of dark energy and matter. You can start here, foundation understanding, comprehensive overview, contemporary relevance, the interplay between dark matter and dark energy, theoretical insights. Now, again, there are lots of further nuances in here which we have to play with. Like, for example, how do I make sure that the follow-up questions, it only still leverages probably some other knowledge base, or when I ask some. So there are other factors which have its own system architecture, system knowledge around it. But for a basic example, I think everyone probably got how a basic RAG system mainly works. So it's a retriever which helps an LLM knowledge base with a particular context or a particular knowledge which is relevant to the problem that we are trying to solve. And post that using prompting and other strategy, we make sure that large language model ends up using only that context to answer the questions which are relevant. Alrighty. Things that we are going to cover in this video are RAG evaluation. We'll go a bit deeper into how to evaluate a RAG system. Second thing is RAG architecture. We'll try and understand some patterns that are probably important when you're trying to architect a RAG system. Then we'll delve deeper into the world of retrievers. RAG system is essentially a retriever system augmented by a large language model. We'll try and understand and look into different types of retrievers, their advantages and disadvantages. We'll look at full text retriever, semantic retriever, when to use each of them. And then we'll also look at a hybrid retriever, which is a blend of different types of retriever as text and semantic. We will close this video by building a project where we are going to build a retriever. Okay, we'll build a text retriever, we'll build a semantic retriever and a hybrid retriever, so that we understand and are the basic that are needed to build the subsystem of retrievers, which can be further added to a large language model and augment the generation as we move forward into this video series. So yeah, stay tuned, plenty in there, and let's get started with understanding RAG evaluation. Alrighty, before we delve deeper into the evaluation of RAG system, a quick revision of the subsystem that we discussed in our last video. Now, any RAG system will particularly have a user input. Okay, I'm calling it UI here. It's coming from different user experience, different UI interfaces. It could be a chatbot, it could be an underlying system through which we're feeding data, from which essentially it could be a query. Okay, it could be a query, it could be any kind of use case that the person is trying to solve, which is sent to the retriever, and the retriever will try and fetch the documents or the corresponding knowledge that this person needed for answering the original question from the user. Now, this is one part of the system. Okay. Second part of the system is where we send this retrieved text or retrieved information, okay, to the large language model along with the original query. And then the large language model has a task where, based on the original query and the retrieved context, it needs to generate a response which should help it solve the corresponding problem that a user is trying to solve. Alrighty, absolutely simple. The way any RAG system per se works. You might see lots of different variation of these, but in essence, at a high level, this is how a RAG system is supposed to be working. Alrighty, now it looks very simple. Okay, there is just two subsystems. There's a retrieval, and then there is generation. We get the corresponding chunks of information that we need, add it to the large language model, give it the corresponding context, and it answers, right? But there are lots of places things can go wrong. That is where the evaluations come in. Okay, if you think of it, which are the places the evaluations might be able to help us? Again, going back to the same system diagram that we were looking for. If you think of it, we are actually working with multiple stages of information. So I normally try to think of it as a subsystem level information flow, and where we can kind of we are not able to capture the corresponding data points that are needed to answer the questions properly. One of those references that I normally suggest everyone to go through is the Raga's paper. Okay, it's a great paper that came out of Cardiff some time ago, and it essentially it tells us is any RAG system per se should be evaluated based on three important factors. One is faithfulness, where what it essentially it means is that any answer that we are getting should be inferred from the context that is being fetched by the corresponding retriever system. What it means is, like, for example, in the use case that we are going to see right now, that is the same use case that we basically saw in our last video of our archive data set, which has like lots of academic papers. If I'm trying to ask a question about, let's say, neural nets, which are used in a large language model setting, I'm just taking a random example, and I'm asking it to a particular question, the answer should be there in the context of the retrieved data that is being got to the large language model. All right, it should not, the large language model should not answer the question. We are actually working with multiple stages of information. So I normally try to think of it as a subsystem level information flow, and where we can kind of we are not able to capture the corresponding data points that are needed to answer the questions properly. One of those references that I normally suggest everyone to go through is the Raga's paper. Okay, it's a great paper that came out of Cardiff some time ago, and it essentially it tells us is any RAG system per se should be evaluated based on three important factors. One is faithfulness, where what it essentially it means is that any answer that we are getting should be inferred from the context that is being fetched by the corresponding retriever system. What it means is, like, for example, in the use case that we are going to see right now, that is the same use case that we basically saw in our last video of our archive data set, which has like lots of academic papers. If I'm trying to ask a question about, let's say, neural nets, which are used in a large language model setting, I'm just taking a random example, and I'm asking it to a particular question, the answer should be there in the context of the retrieved data that is being got to the large language model. All right, it should not, the large language model should not answer the question based on its own internal knowledge. Alrighty, that is what faithfulness essentially means, and that is what how I interpret it. Second is answer relevance. Second thing is that the answer that large language model is generating should be relevant to the question that is being asked. Okay, maybe the context that we have is quite good, it's getting added to the question, but the answer that we are getting is just not relevant to the problem that our user is trying to solve. And third is context relevance. Alrighty, the context relevance essentially means is it tries to solve the subsystem of retriever. Essentially, the context relevance is that the context that a retriever adds to the original query should be relevant to the question that is being asked. Alrighty, I said lots of things. Now, again, going back to the same thing, think of it in three particular aspects of it. Okay, like first, think of number 3, context relevance. The context that is being extracted from the knowledge base should be relevant to the question that is being asked. Second, answer relevance. That a context plus question should be able to satisfy the user's need. And third is faithfulness. Faithfulness essentially means is we should be able to answer the question only based on the retrieved context from our knowledge base. That is, at no stage we should expect an answer which is either getting completely hallucinated by a large language model, or is coming from a totally internal pre-training knowledge that has been learned over a period of time. So hopefully that makes sense. And I'll just to make it a bit more concrete, let's look at a quick example, right? Same example that we saw in our last video of archive data set. I have already done the pre-processing where we have done a TF IDF of the whole data set, and it's being stored as a vector. So I won't go into the detail anyway. The code will be available for everyone. But what only change that I have made is I've added a print retrieve paper so that we are able to see the context that gets added to a particular question, and accordingly we can make a judgment or try to understand how it's doing on all the 3 parameters, right? Again, 3 parameters: faithfulness, answer relevance, and context relevance. Alrighty, okay, so we have done that. What I will do is I will rerun this. Okay, so we have it here, and let's ask it a question. The question that we might probably want to ask is, can you explain chain of thought in LLMs? Okay, what happened here? Alrighty, the asked question: can you explain chain of thought in LLMs? Let's see. Okay, so we've got chain of thought prompting is a technique used to enhance the reasoning capability of large language model. It involves guiding the model to generate. This method has been given significant attention because it has been shown to elicit impressive reasoning capability. Key concept: chain of thought, sequential reasoning, structured input, demonstration, valid and invalid example, application across domain. Yeah, so answer looks really good for me. Now let's look at the paper that it has got. The paper that it has pulled in, and paper number 1 is Beyond Chain of Thought, a survey of chain of X paradigms of all large language models. Contrastive chain of thought prompting. Shut up and let me think of why you should work on the foundation of quantum mechanics. I don't think this is relevant. Anyway, it's paper number 3. So with respect to the trying to evaluate this just based on this one question, okay, think if this is a rack system, again, understand I'm just trying to make this judgment based on one question. Ideally, the way we will do it is we will have a test data set or test set of questions, which we will try to do the same thing that I'm doing right now. So first let's look at answer relevance. Okay, so can you explain chain of thought? Okay, the answer to me looks quite relevant, and I'm quite satisfied with it. So a complete take on that. Second, context relevance. The context that is pulled is Beyond Chain of Thought, survey of chain of X paradigms for large language models. So I do reckon it pulled a good paper to understand chain of thought or explain chain of thought to me. And probably the third is faithfulness. Okay, this is something that we need to understand. chain of thought has been a widely adopted modeling method eliciting. Let's look at this paper. Okay, so ideally what I'm trying to understand is okay, so it's a chain of thought is a methodology that substantially enhances the reasoning capability element introduced by was prompting LLM with a structured format, input, thoughts, output. Okay. Alrighty. Now we'll spend some time understanding some intuitions behind building a good RAG architecture. Most of the things are quite intuitive, but it's always good to revise them before we delve deeper into building great RAG systems. As I've discussed before, a RAG system in itself is a system of systems where there are multiple subsystems which needs to be optimized properly to get a great RAG system. Now we'll look at these subsystems, get some intuitions around what needs to be really ticked off before you kind of start building and integrating them together. And hopefully that helps all of us build great RAG systems. So going forward with that, any RAG systems in essence will have an LLM as the generator. Okay. Then it will have a retriever. Now, retriever can be designed in multiple ways. As I discussed before, retrieval systems have a great history. It's not something new thing, but there are multiple ways it can be done. But the two major ways retrievers are designed are full text search, a full text retriever. The second is semantic retriever. Okay, and then there is another type that is called as hybrid. Okay, which is a blend of these two. Now we have an LLM, we have a retriever. What else do we need? Third thing that basically I try to think about it is what I call as pre-production stage. Okay, pre-production stage. Pre-prod. Pre-prod stage is a stage where we get our retriever in shape so that it's able to get us the information, get us the context that a large language model might need at runtime to give a right answer. So at pre-production stage, things that need to be done are information extraction. What it essentially means is, like, for example, you're building a chatbot for documentation of a coding repo. Then how do you take that information and pass it into a form which could be leveraged by a technology system? Okay. Second thing that needs to be done is something that's called as chunking. We'll discuss it in one of the future videos, but chunking essentially means is, suppose you have a 500 pages PDF, which is your whole information or the knowledge base of your organization. How do you split it into good intelligent chunks, which could be added to the context of a large language model without overwhelming the context and without overburdening on the cost, essentially per token cost. And final thing that's probably extremely important that we have also covered in our project of the first video is indexing. That using probably one of the different retrieval methodologies, how do you index your knowledge base in a form so that it's very easy to retrieve the corresponding right knowledge when a question arises from the user. So that's in essence is you should probably think of a RAG architecture, that you have to decide upon a large language model. Okay, which large language model you have to choose. You have to choose on a retriever, and which retriever essentially works for your use case. And then you have to kind of make some decisions around the pre-production. Now, I didn't speak of the large language model in here because the assumption is most good large language model that you will probably use, whether it might be a Claude, it might be a GPT-4, or should do a decent enough job for you. But few of the consideration that you should always have when choosing a large language model are cost. There might be some use cases where when you delve deeper into it, a large language model might be just there to give a good user experience. And most of the good work essentially is happening from the retriever. So you might want to find a large language model which might be really optimized on the cost and can really convert the knowledge that it receives from retriever into a more digestible form for the user. And second, essentially, this you should probably also always think of is latency. Alrighty. Now, depending upon what's your use cases, whether you want to host a large language model yourself or use one of the cloud providers, you might want to think of latency. Like if it's a chatbot that you're deploying, you might want a large language model that has really low latency. So you might want a small large language model deployed on your own cloud servers and so on and so forth. But yeah, that's about it. I think these are some things that I wanted to cover. That you have a large language model, you might have a retriever, and you think of something called as pre-production, and then based on different parameters, you might want to make all of the decisions. Most of these things will become much more clear as we keep on designing multiple systems, as we evolve this series of videos. But just keep this in mind. A RAG system essentially has a large language model selection that you need to do, has a retriever selection that you need to do, and how do you, and a pre-production phase where you need to decide how do you pass the information of a knowledge base, chunk the information, and index it. Okay, so that's about it. Alrighty, so before we delve a bit deeper into retriever systems and types of retriever systems that help a RAG system become much more productive and efficient by identifying and adding the correct context to the large language model when answering a query, we should just once more spend some more time on retriever system, okay, and how it might look like. So this time we will go a bit deeper, okay. So in essence, without even thinking of large language model, a retriever system is based on a query or an information that is being probably punched in somewhere. Now this information system, this information hits the, what I should say, backend of the retriever system, which in essence has three main blocks, okay, which I've mentioned here. There is a first stage, there's a re-ranker, and there is modifier. Now all of these three together help us get the correct information or the correct context that's needed for that corresponding query which a user is trying to answer. All right. Now, this whole retriever backend is connected to a knowledge base, and this knowledge base, there is another step which we'll cover as we move forward in the lecture, in which the knowledge base is converted into a form which is more suitable for a information retrieval system. Some of three main steps that you have to think of that we also discussed in the just few minutes back in the same video was information passing. Information passing is essentially data that is relevant for a retrieval system might be available in multiple ways. It might be in tables of SQL data sets. It might be in HTML files, it might be in XML files, but how do you pass it into a form which could be stored and readily accessible for the retriever system for to use it? Second is chunking. Now, if you think of it, if going back to a past example, archive papers, there are multiple ways you can literally think of information across papers, right? You could literally bunch together 3 or 4 papers from one particular stream into one, and that could be your one chunk. Or you could take one paper and split it into multiple different paragraphs, and each of them could be a chunk. Ideally, there is no right or wrong way of doing it. It all depends upon your use case or the problem that you're trying to solve. But in essence, it's said it's better off to store concrete chunks of information which can in themselves provide a sufficient amount of information to answer any particular query. Now, there are multiple ways of doing chunking. We will also go to that. And finally is indexing. Now, all of the information that you will have, whether it might be text or whether it might be some other multimodal images or videos or so on and so forth, they are all stored, but they need to be indexed and stored. What indexed and stored essentially means is indexes is a way of storing a data that allows us to later on go and retrieve it in a very, very efficient way. Okay, indexing is not particularly only from computer science space. It basically started off in multiple other different streams, where it might be libraries where there are multiple books and you want to have a particular index so that you can go and basically get the right book, and other multiple places. So anywhere where you have to retrieve from a huge bunch of information or huge bunch of IDs, also I should say, this should be a way you should index them, so that like you can easily go and search for a corresponding whatever you might need. Now that is in essence is indexing. There is multiple ways in indexing is done in the industry. We have all moved to a stage where most of it is being captured by the semantic retrieval or using large language models, but still I do think there is also benefit in understanding some of the basics around indexing, because sometimes even the simple indexing methods work great for you. So in a sense, going back to this big box of the retrieval backend, there are three main small blocks in there. First is first stage. First stage in essence is where when a query comes in, the retrieval system tries to take the query and tries to find the top candidate chunks from the knowledge base, which might be closer to the query or answering that particular query, right? It doesn't try and get the perfect answer, but tries to get like top 5 or top 10, depends upon how much you are concerned about latency and other factors. But that's what basically the first stage is. Second is re-ranker. Re-ranker is where we actually go on and take, you have your own way of taking those 4 or 5 different candidate context and converting it, or selecting one particular context that could be added to a large language model. And finally, modifier is where you actually take the final context and modify it in a way which might be suitable for the downstream large language model to act on and generate a particular output. So in essence, this is a retrieval system. I've gone a layer deep so that you actually understand how a retrieval system basically works. Again, just quick revision. Query comes in. There is the first stage which takes that query and tries to find from knowledge base top candidates which might answer that query. Re-ranker that takes those candidates and gets or either compresses them into one, or tries and find one particular context that might be suitable for the query that we are trying to answer. And finally is modifier, which modifies the context in a way which might be suitable for the large language model. So in essence, this is a retrieval system. Now let's go into details. Alrighty, now let's look at some types of retrieval systems that you will find in the wild. They are majorly, you will find either of these 4 retrieval systems when you are trying to build a retrieval system or working on retrieval systems. And each of them have their own pros and cons, and which we'll also discuss further in the video. But just right now, what I want everyone to do is just try to build an intuition around all of these, right? So essentially, there are 4 types of retrieval systems. First, exact or Boolean search retrieval. Second, full text retrieval. Third, semantic retrieval. And fourth, hybrid retrieval. Alrighty. Now we'll talk about each of them now in detail. We'll start off with exact or Boolean search retrieval. Okay. So the exact or Boolean search retrieval, in essence, is where you write a particular query, and some of the different corresponding subjects out of it are directly used in a Boolean equation, search from a particular text or search from a particular database. It's as simple as that. Think of it like literally if those of you who are familiar with SQL, how you in a SQL you query a particular database to get a particular row. That's probably a example of a Boolean search. Now there are further processing steps that are involved within it, where a query is taken, it's probably stemmed and lemmatization is done, and you probably identify the subject and then you put it into a Boolean search. But in essence, that's what it is. It doesn't search for the whole context essentially, or like for example, if someone is asking what are some top restaurants in Australia, the whole exact search engine particularly is only probably meant for where it looks at it, it converts and gets it and sees Australia and basically plugs it into where you need it in a country format. So that in itself is exact Boolean search. Second, we'll look at the full text search. Full text retrieval is what we have been doing so far in some of the examples and projects that we have been building in the video, where the knowledge knowledge base in itself is converted into term frequency, inverse document frequency, sparse vectors. Sparse vectors are because, like for example, if you're looking at a particular text chunk, out of all the different term frequencies or different words, most of them will be zeros, right? There are only few places where you will see one. Therefore, it's called a sparse vector. And you mainly take the query that you get and you use cosine similarity to identify that which of the chunks stored in knowledge base are closer to the query that is being asked. That in itself is a full text retrieval. Third is semantic retrieval. Semantic retrieval is something that's probably the most popular right now, where the knowledge base, different chunks of the knowledge base are converted into vector embeddings using deep learning models. The reason why it's become more popular, and probably you will see it topping the charts of the metrics across different retrieval systems, is the deep learning models convert the knowledge chunks into a better representation of the overall language and overall understanding of it. Like for example, it could help you understand whether a king and a queen both are probably somewhat, there is a similarity between both of them. I will link some papers down below, people who are probably interested in understanding embeddings and all of this stuff. But this is how it is. This is more of a dense vector, and you mainly to search through it and to identify the candidates and do re-ranking. Basically, different other methodologies like in approximately near neighbor, fast, and different other terms and things are used that we'll further see as we move in the lecture. And finally is hybrid retrieval. Hybrid retrieval can take multiple forms. Hybrid retrieval in essence is where you try to take the best of, let's say, semantic search as well as text search as well as probably exact search, and depending upon the use case you might use all of them. And like for example, in first stage where you are trying to get candidates before the re-ranking, you might just use a full text search and get the candidates. Post that, you might use a semantic search to re-rank them and basically then send it across to a large language model. Second way it can be done is you can come up with a score, and that score could be based on full text search as well as semantic search. You add them and basically then send it across. Multiple ways it could be done, depends upon your experimentation and how do you model it. So this in itself is how 4 different retrieval systems essentially exist, and everything that you will probably see basically will fall in these 4. The most popular right now are probably semantic search and hybrid retrievals, and which are probably topping the charts across RAG systems, which we'll be looking at in much more detail as we move forward. Alrighty, so before we proceed and do some examples and quick implementation of some retrieval systems, let's quickly again compare all the 4 types of retrieval systems whom we just saw. So starting with the exact match, its key feature is strict quality based retrieval. Second is full text search, which searches through your corpus using keyword and relevance ranking like TF-IDF, term frequency, and there are multiple ways of doing it. Semantic retrieval, it's meaning based and embedding similarity, right? So it allows us to find different sentences, although they might not be textually similar, but semantically or meaning wise they might be similar. And finally is hybrid retrieval, which tries to combine all the different retrieval types that we just spoke about and tries to get the best out of it. The strengths are exact match is absolutely fast and precise. Most of them that I've seen actually use SQL engine underneath it, and probably SQL is one of the most tried, tested, one of the most robust system in the world. Extremely fast and precise. You can optimize it as per different data types and so on and so forth. So extremely fast and precise. The limitation in that is there is no flexibility in query variation. It literally is there is a templated queries that exist depending on the questions that are coming through. You just plug in the particular Boolean algebra in there and just change few stuff and just basically run it. So it's a bit we'll say unsophisticated, but it's extremely fast and precise. Full text search is good for unstructured data, but it doesn't have limited semantic understanding. Like for example, things like if you're asking for who are the closest monarch to the King of England, you probably might not get anything in the corpus if the words like monarch or king doesn't exist in a corpus. It might have something else. It might have leaders closer to the King of England or something like that. Third is semantic retrieval. It captures semantic relationship really well, and that's the reason why you will see most of the semantic new retrieval system implementation, almost all of them, whether it might be a search or it might be a document lookup, they all try to use semantic relationships. But the limitation is it's quite computationally intensive. You need a deep learning model to continuously keep on changing your embeddings and basically keep on updating them. And finally is hybrid retrieval, where based on your use case, you might use just a little bit of semantic retrieval and the rest of them might be an exact match or full text search or the other way around. But the limitation with the hybrid retrieval is the complexity in implementation. There is more work that is needed in terms of the engineering and designing different smaller systems, different data flows, and that takes a bit of work. So yeah, these are the 4 retrieval system. Keep in mind, think about all of these whenever you have a retrieval task in your hand and try to implement them. Now let's look at some examples finally. All right, so now let's look at some examples on implementations of retrieval systems. So this is something that I have already built. We'll go through the code in a bit, but in a sense, it's a kind of a, like I should say, mock mini search engine based on the same archive data set that I mentioned before, and we have probably leveraged in the first video and probably even in the initial part of this video. But this is mainly a search engine which allows you to search through that corpus using all the 3 major functionalities or 3 major types of search: semantic search, BM25, this is a type of lexical / textual search, and exact match. Okay, and what we'll do is we'll do this, and it will, over a period of time, as we do this, it will become apparent of what each of them does and what are the benefits of each of them. Okay, so the query that I'm trying to find is among all the archive papers is logistic regression based finance models. Okay, so let's see what kind of search it gives us. Click it. Oh, sorry, we are doing exact match. So in the exact match, when we are doing logistic regression based finance model, we didn't get anything, like literally anything. So essentially, because what exact match does is it goes in and like literally searches through the abstract of all the papers that are in this data set. Is there something called logistic regression based finance models? If it doesn't exist, no search results. Okay. Now let's look at BM25. Okay, what do we get? Okay, so we've got some stuff like, for example, we've got integration, non-stationary time series, stationary, non-stationary increments. In this, we have like a regression written somewhere. So maybe that's the reason why we are getting this. But still, last image integration was largely for this, and it's okay. It's something, but still a flexible Bayesian generalized linear model for dichotomous response. Application text categorization, again, nothing related to finance in here, but because it has regression and should mention here, we got this. So similar kind of results, not that relevant, but you get what it's, because it's a lexical match or a textual match. It went in and tried to find the corresponding like words like regression, logistic or finance model, but it didn't get anything. Now let's finally look at the semantic search. Okay, let's click on semantic search. Okay, good. Now we are getting parametric and non-parametric models and method in financial econometrics. Quite relevant. Okay, we'll search for logistic regression based finance model, because what semantic search does is it doesn't try to match words in the search corpus, but tries to find corresponding semantic meanings. So because I'm using logistic regression based finance models, it's looking for parametric as well as non-parametric models in there, and then it gives us quite a decent enough first paper. Second is again trading strategy based on the second law of thermodynamics, which I still feel is quite relevant. Prey model for stock market fluctuation. So most of them generalize half logistic distribution authors. So quite relevant. I would say at least from one example that we just saw, the semantic search is giving us quite relevant answers, and that is the reason semantic search is literally ruling the world of retrievers, or ruling the world of retriever search. We hardly find anywhere where people are not doing semantic search. The only reason that you will find it is if your corpus is really small, really narrow, plus you don't want to have so much investment on your like processing power and so on and so forth. We already had a look at that table which told us what are the advantages and disadvantages of that. So this in itself explains you all the 3 major types of retrievers and how do they help you and what they can do for you. Now in exact match we didn't get any output. Let's try and let me show you something. I will take this on type 3 or something from a particular paper and see Dynamics inspired. Maybe we do the predator prey population evolution. Okay, and let's see what do we get here. And we do an exact match. So predator prey model for stock model fluctuation. Present a dynamic model for this. So as you see, like it goes in and searches for the exact match in there somewhere. So in here, if you go through it, oh yeah, so it literally went in and searched for one and found it in this particular paper. The population evolution is in this abstract, so it gave us that output. So that's what exact match does. Now let's quickly have a look at the code. I will anyways have this code mentioned in the description of this video, so you can have a look at it. Pretty simple code. What it literally does is it uses BM25 semantic for semantic search. It uses sentence transformer, and for exact search, it's literally a simple search for a string if there is a particular word that exists. Then it's a normal Gradio-based interface which tries to use all of them and runs the search on the abstract, not on the title or anything else. So that's about it. I think in this video we did really well. We further went deeper into the retriever aspect of retrieval-augmented generation. We understood how important that is. Now, if you see right now, this in itself is a discipline. It's a wider discipline. And on top of that, what a generation or LLM-based generation does it makes the user interface much more clear. So just keep that in mind. We will further delve deeper into how the retriever and generator work together and how do you further try to optimize the whole system as a lot. But always what I suggest is always start with the retriever first. If you are working with the absolutely greenfield problem, start with the retriever first. Build a gold standard data set. Ideally, the way the evaluation will happen, like what I did here is we just picked one or two queries and saw, like, from human, that is my judgment, if it's working or not. But ideally what we will have is you will always have a gold, what I call a gold test set, in which you will have, okay, for this kind of query, this is the corresponding ranking that I should expect from the corpus, and then accordingly you will probably see what are you getting out of a particular retrieval model, and then do something like a pearson correlation or some other metric to check if it actually matches with what a human might actually expect. Hey guys, what's happening? So welcome to this video where we're going to discuss multimodal RAG systems. We're going to keep it really simple and more intuitive for everyone to understand. Why do we need multimodal RAG systems? How can we implement it? And what are some nuances needed to develop it well? Now, before we delve into it, what is multimodality? For those of us who don't understand it, multimodality in any system is where it's able to work with different modalities in which information is captured. Different modalities means text is a modality, audio is a modality, image is a modality, video is a modality. So all of these have different ways in they capture information about anything that's basically happening around us or in a system. Now, a good retrieval system or a good information system should be able to work with all of these different modalities. This is how and why we are building the multimodal RAG systems. Now, in this video, we're going to cover it across 4 different segments. Feel free to scroll through all of these through, depending upon what might interest you or might bookmark it, come back to these things and just review it whenever you are building something. We're going to start off with why do we need multimodality in RAG systems? We are going to go into a bit of a deep dive into architectural consideration of a multimodal RAG system. Then we'll spend some time thinking of some design patterns that we see out in the wild and some successful design patterns that I have seen people implement when they're implementing multimodality in a RAG. And finally, we will build a multimodal RAG system right from scratch, and hopefully that should be really good. And yeah, let's go. Alrighty, so let's start with understanding the why behind why do we need multimodality in RAG system. The answer comes not just for RAG, but for any information system that exists today, whether it might be search, whether it might be simple retrieval system, whether it might be normal information with a person presenting to another person. It has been observed that any communication or any information is more effective. It's said to be it's around 66% more effective when you had multimodal information that is being shared, right? Like, for example, when you're presenting someone, it's always good to share an image or a chart with the person so that they're able to understand what you're talking about other than text only or just conversation only. So in that way, essentially, there have been multiple scientific experiments which actually tell us that a multimodal system or multimodal information system is much more effective in making a user happy or making the query answers to be more effective. It's said to be most of the information that exists on the internet and is being created today is not text. It's audio, it's video, it's image, it's probably sensor data, and so on and so forth. So when we are developing a rack system, if we are just looking at text only, we are leaving lots of value on the table, right? Again, it differs a lot. There are some industries, let's say legal, probably banking, which are extremely text heavy. Okay, we probably won't find any image data in there. We will probably have some audio data from customer service, but still, all of those a little bit of data that exist in there has lots of value in there. So a rack system or any system essentially will should always consider or try and be multimodal, so it's able to get value from all of these more different modalities. Alrighty. So yeah, with that, let's move into understanding some of the architectural consideration of multimodal rack system. Alrighty. So let's develop some intuitions around the architecture consideration that you will need when you are building a retrieval augmented generation system with multimodality at its core. Now, the first thing when you're building it, what I will suggest everyone to do it is just think of all the different modalities that you will probably have in your information capture within the business as documents, right? Like probably a text is a document, an image is also a document, a video is also a document when it's stored in a document retrieval system, and same is with any other modality that you can think of. Now, the biggest thing that you're building a retrieval system is you need to develop an index for your whole corpus, right? You need to have an index for your images, your audio, your video, and so on and so forth. So in that essence, there is not much of a difference between the overall system consideration between a text only or a unimodal system compared to a multimodal system. The difference comes in is different subsystems that we want to build properly so that different modalities can work together. Okay, let's look at this small architecture that I put up from this wonderful blog by Langchain. It's called Semi-Structured Multimodal RAG. Really great blog. I recommend everyone to read through it. Here, what they are kind of showing is if you have a document, right, and in this instance, it's an academic paper, right? In that academic paper, there will be tables with structured information. There will be text. There will be images, right? Now, all of these three are different modalities, and all of these three will have its own context and own information that they're probably sharing with the user who is probably reading that paper. So to think of it, something that we have discussed before, one thing that needs to be done is indexing, right? And how do you do indexing is the main core of a multimodal system. Now, in essence, here what they're doing is they're just passing all of these three different modalities through an LLM, and it creates a summary for all of these three: images, tables, and text, and stores the summary in a vector store and stores the corresponding and linking to that summary with an index into a doc store. Like for example, if the summary is a picture of Mona Lisa, right? That's probably a summary, and it has, let's say, index of XYZ, and that corresponding index is actually stored in a doc store. So whenever someone refers to that particular summary, they can refer to that particular doc store, right? This one something to understand. Same thing with the table, right? You might have a table which might be different training data used for different large language models, and it might have that might be a summary for a table, and that table might be stored in a structured form into a different sequential table, right? Essentially. So that's about it, and how you might have to think of indexing different multimodal systems. Now, what happens in production is when a question goes out, right? When a question comes through a retrieval system, that question, similar to how we discussed in the retrieval system in one of our past videos, we have to find corresponding document chunks in our system, in our corpus, which is now multimodal, which could help answer the corresponding question or the corresponding information that is being seeked by the user. That's about it. And that question basically hits the vector store and tries to find the relevant summaries. And correspondingly, it actually sends the corresponding documents along with the summary to the large language model, which can accumulate that together and provide a good response to help the user out. So this is just one of the patterns, architectural patterns. But the thing that I want everyone to remember is think of a multimodality as different sets of information for which you need to give a corresponding text or embedding summary to the user. All right, and to do that, and because large language model is mainly in most cases is a text only system, we also have multimodal models. So you have to find a way of converting different modalities to either text only or to embedding only into a form which a large language model can digest to give a response. So, this is just one of the patterns, right? Because here they are not using any embeddings per se; they are just using large language model to summarize the different information modalities. We'll also look at some other modalities which are become really popular and how they might actually help you develop a robust multimodal system. Alrighty, so let's look at some design patterns that are emerging right now. Now, one thing that I want everyone to understand is multimodality in the RAG space or in retrieval space is a constantly evolving field, right? So I will talk about three main design patterns that I have observed which have worked successfully in a retrieval augmented generation space. There are also multiple other design patterns that people have come up with, and it might suit their use cases. But yeah, means if you're building something, please try one of these three, and I'm pretty sure it might probably work out for you. This or one of these variations essentially. So let's start with that. The first one that we already saw in the architecture section that we discussed is summarize, and then generate. Okay, in this space essentially depending upon you might have whatever modalities you're working with. Ideally I suggest not to work with more than three modalities at a time. Let's say you're working with three different modalities. It might be image, it might be structured data, it might be text data. We will find either a single LLM or multiple LLMs which could summarize whatever information is captured in each of the corresponding chunks. And that summary in essence becomes the index of that information snippet that you have captured. Cool. And we stored it into a vector database with an index linked to a document store. And when a large language model wants to generate based on a question that comes from the user, the retrieval system, based on the question, it tries to find a similarity between that and the corresponding summaries that are being stored. And in this case, you can do a retrieval in any of the ways that we have discussed in the past. It could be an exact search, it could be a full text search, it could be a hybrid search, it could be a lexical semantic search, depending upon your different use cases. And then it correspondingly feeds the large language model different information summaries from different multimodalities, right? And at that moment of time, the large language model will have quite a good corpus of information. Based on that, it can generate output. All right. Now, different organizations do it in different ways. I've seen people who actually fine tune a large language model to do this for them. There are also people, you will find lots of great large language models on the Hugging Face, which are pre-trained to do it, pre-trained to do for audio embeddings, text embedding, structured data embedding. But this is one of the good patterns, quite a simplistic pattern, because there are already summarization is already quite a evolved space in most of large language models. So you should probably see good decent outputs in here. Now, second pattern that probably what we'll discuss is what I call is multi-embedding and then generate. Okay. What does multi-embedding and then generative essentially does is it will depending upon if you have like two or three or let's say four different modalities, you will try to find a corresponding one single embedding for all of the modalities together. Alrighty. So instead of having let's say you have let's say a picture followed by a text snippet followed by a structured information, and you are chunking them all of them together. This trained large language model is able to compress all of these three information together and create a single embedding for them. So this text chunk essentially gets stored in a this text plus image plus table chunk gets stored together in a database, and the corresponding index becomes this multimodal embedding. And this multimodal embedding is always leveraged whenever your question is asked and you find a similarity between that embedding and the corresponding embedding that gets created of the question. So the thing to remember is what the multimodal embedding does for you is you don't have to like manage multiple embeddings of different modalities. You can have just one single embedding which can help you across all of these three different modalities. Number three, single embedding per modality, then generate. Single modality, again, hopefully quite a simple way of thinking of. Each modality will have its own embedding model. It might be a clip for a image. It might be some other different language model for audios. It might be something else for structured data. And each of them will create a corresponding embedding, and we will have a different embedding stored across all of these three. So the disadvantage of this is you will probably end up having a huge good big vector store essentially, so lots of spend on the vector databases. But the good thing about it is you are able to cater to the individual niches of different modalities when you're calculating embeddings. So although the processing, so there will be expenditure on the processing side, managing of different embedding stores, managing of different modalities, but the pro is you are able to create a much better balance of different modalities and get the corresponding benefit that is needed when you're actually working with multiple modalities. So that's it. There are also multiple other design patterns that you can think of, but these are the three main design patterns that I have observed and I have tried out, and which all of them end up working quite well. But what we'll do is we'll pick one of these and build a project around it. So yeah, let's go. So let's look at a small project. In this project, we are going to develop a multi-model rack system. We'll first of all develop just a multi-model retrieval system, and then go forward and stack a large admin model on top of it. The dataset that we are using is a really nice, nifty little dataset called as fashion product images, and it's on Kaggle. It is a combination of a table which has all the description of a particular product image. It has things like category, subcategory, the seasonal collection from where it is, and a short description of it. And then we have a folder which has its corresponding images. For my convenience, what I have done is I have taken that particular data set and I have reduced it to just 50 records. Okay, so here is what we have done here is we just reduced it to 50 records, which we are calling as a mini fashion product data set, which has just 50 images and its corresponding 50 rows with category, subcategory, and all the other details. Now, how does it actually look like? So this is how it basically looks like. Like for example, for product display name Peter England Man Party Blue Jeans with a base color of blue, season summer year 2012, you will probably have an image like this. Good. So now that we have a basic understanding of the kind of data that we are looking at, first step is we'll develop a multi-model retrieval system. All right. Now a multi-model retrieval system, what we are going to use is Clip, a beautiful multimodal embedding pre-trained model released by OpenAI. Kudos to them. Probably it was released very early on when multimodal Gen AI was becoming a thing. Go and check out the paper. Still a great paper to read through. And we are going to use ChromaDB. ChromaDB, a vector database that allows us to quickly vectorize different multimodalities and do a quick vector lookups. So ChromaDB.client, we are reading the style mini.csv, which is a Excel file, reduced Excel file, just 50 records in there. And for each item in the style mini.csv, what we are doing here is we're getting the corresponding image path. Okay, the image path is essentially the row ID in there .jpeg, and we are from which we are getting the image. Now we are creating the image embeddings for these. The image embeddings we are creating is we are using the clip model and getting the image embeddings. And finally, we are concatenating all the important parts of the text that we have. We're getting it from, so we are using product display name, master category, and subcategory. And we are using all of these and creating something in Chroma that is called collections. Collections is, in essence, you can think of it as a multi-model embedding space where it maps different modalities, in this case, an image and a text, into a single embedding space. Cool. Now that one, so here we are doing it for the images and the text. Now that we have done that, our retrieval system is ready. Now in this retrieval system, let's try a few examples. What I want to try and do is I want to just search for things like jeans or a shirt and see if it's able to give me any results, right? Again, remember, ideally something in production will be a much better than what I will show you here because I'm running it on my MacBook Pro. So the example and ability of them is completely limited. But yeah, still a good example to show you how it works. Find similar items. What it does is, depending upon the query that we are sending across, if it's a query's image path, it will take that image, convert an embedding of it, and find a corresponding similar embedding in the collection, in the ChromaDB collection, and give us the corresponding image. If it's a text, same thing. It converts the text into an embedding, finds the multimodal embedding in the chroma DB, which is closest to that text embedding, and gives us the output. Very simple. So now it allows us to now this multimodal embedding works across two modalities for us. So you can do things like upload a t-shirt and find similar t-shirts, upload a pant, find similar pants, and so on and so forth. So let's do that. So like in here, what I'm trying to do is I've already done something. I'm trying to look at a t-shirt. So I'm just look at query t-shirt, text t-shirt. Okay, so I got two t-shirts, one by a male and one by a female. Let's look at something called as just shirt. Let's see what we get. Okay, we don't get any. Remember, again, we might not get. We might just have one shirt in that database, in the 50 database, right? So first thing that we got is a shirt. That's not bad. Now let's try another example. So what I want to use is I want to try and use an image as a lookup. Okay, so we're going to use probably 49, which is a belt. Okay, a formal men's belt. And when we look at the formal men's belt, it gives me three different things that look like formal belts. Okay, so not bad, right? So it gave me something similar. Now let's look at something else. Let's try something else. We'll look at the record, let's say 39 in the 50 limited record that we have. Nice. So we had the image that we are looking up with is this lady wearing this, I think, pink t-shirt. And okay, now what we have is we have three different women apparel, a t-shirt, something similar t-shirt, and another dress that a woman is wearing. So good. This retrieval system is working quite good, particularly considering that we are using a pre-trained embedding model, and we are just working on 50 records, right? Alrighty. So now let's convert this retrieval system into a RAG system. So for a great user experience, the only thing that we need to do is we need to stack up a large language model on top of it, and we have to make sure for any query that comes out of the large language model, whether it might be we are it might be, okay, can you help me with something like this t-shirt or this pant? We should be able to find a corresponding answer in our database, in our vector DB. Similarly, another thing that we have ability that we can now add to our retrieval system is we can allow through the large language model interface someone to upload an image, and that image will go to the retrieval system, find the corresponding text, and give that text embedding in as a context to a large language model, and we will have a better context for large language model to answer. So let's look at it. So we are using GPT-4 Mini. I won't bore you through all the code that I wrote, but a simple call of a GPT-4 Mini, and where the context gets added depending upon the query that is being asked. So the only thing that's happening is the query is being leveraged by the Chroma Vector DB to look up into this multimodal embedding space and find a corresponding embedding which is closer to us. And depending upon whichever is closer to it, it will give us the overall text description, everything around that particular embedding function. And we have this beautiful radio kind of a chat thing that we have created. What we'll do is we'll click something and click and upload something, or maybe we ask something. Ask me about fashion recommendation. Can you recommend me a pant? Okay. Oh, some problem. Let me try again. Recommend me a pink ladies t-shirt. Okay. GLS 221 women's pink t-shirt is a great choice for a stylish and casual look. Okay. So this is not bad. Let's look what a GLS 21 women's pink t-shirt. I think we already saw it somewhere. Yeah, here it is. GLS 21 women's pink t-shirt. So when we search for GLS pink t-shirt, this was the first result that came out. So this was added to a context of large language model, and it gave me that output. Right now, let's do one thing. Let's try and search using an image. Recommend me something similar. Ladies t-shirt recommended jealous 21 women's pink t-shirt is a stylish option that can be easily. Let's clear it and try again, okay? Because I want to make sure that we have a fresh way of looking at what we are doing. Alrighty, let's go again. 3954.jpg. Let's look at the again the same t-shirt, woman pink t-shirt. We are uploading the image of woman pink t-shirt, and what we'll ask the bot is, can you recommend something similar from your collection? Okay, sure. Based on the options, I will recommend the following. If you're looking for a casual and stylish top, so it understood, right? So I gave it, converted into embedding, and it was able to uh, learn that what we are looking for is probably a woman's t-shirt. The Jealous 21 women's pink t-shirt. For a more vibrant option, Jealous 21 women purple t-shirt. Okay, W women printed beach kurta. So beautiful. It understood we are looking for women's apparel. It gave us recommendations around that. The large language model has added a good user experience, good human-like conversation capability around it. And remember, we are just working with 50 examples here. Okay, if I convert it, and I will probably do it in one of the later videos on a bigger corpus of fashion or any number of the things, it will give me much better recommendations. So that's about it. That's a really good short tutorial around multimodal RAG systems. Remember, it's still an extremely evolving field. I just showed an example based on an image and a text. You could have video, image, text. You could have multiple 2 or 3 different modalities. But whenever you're building, my recommendation will be always start with 2 modalities. See what are the user experience you're optimizing against, and then build on top of it. So yeah, that's it. This is Shobh signing off. Take care. Chat to you next time. Bye.